from scattered signs and silent rules, from hidden limits beneath free moves. A matrix waits not to be changed blindly, but to be understood deeply. Each flip tells a story, every constraint hides a truth, and sometimes the path to maximum gain is not action but insight. Welcome to this presentation on the problem titled Maximum Matrix Sum. In this problem, we are given a matrix and a flexible looking operation. At first glance, it may seem that we need to simulate many operations or try complex transformations. However, as we move forward, we will discover that this problem is less about brute force and more about understanding a powerful mathematical invariant. Let's begin this journey from constraints to clarity. We are given an n by n integer matrix where values can be positive, negative, or 0. We are allowed to perform the following operation any number of times. We may choose any two adjacent elements, that is, elements sharing a common border, and multiply both of them by -1, effectively flipping their signs. Our objective is simple to state but subtle to solve. We must maximize the sum of all elements in the matrix after applying these operations optimally. The key challenge is not how many operations we perform, but understanding what is fundamentally possible. Before moving further, it is crucial to clarify what adjacency means. Two elements are considered adjacent only if they share a common edge, up, down, left, or right. Diagonal neighbors do not count as adjacent. This restriction is important because it limits how sign changes can propagate across the matrix. Despite these limits, we will soon see that the adjacency constraint is still powerful enough to allow global transformations. Let us look at a simple example. The matrix contains two positive ones and two negative ones arranged diagonally. By repeatedly flipping adjacent pairs, we can effectively move negative signs around the matrix. With the correct sequence of operations, all values can eventually become positive. As a result, the maximum achievable sum is 4. This example hints that adjacency is not a major obstacle when used cleverly. Now consider a slightly larger example. Here the matrix has a middle row entirely negative, while the top and bottom rows are positive. Even after applying operations optimally, we find that one negative value must remain. The maximum sum we can achieve in this case is 16, not the sum of all absolute values. This example introduces an important limitation that we must understand mathematically. Now we arrive at the most important insight of the problem. Each allowed operation flips the sign of exactly two elements. This has a critical implication. The number of negative elements in the matrix changes by 2, not by 1. Therefore, the parity, whether the number of negative elements is odd or even, never changes. This parity invariance is the backbone of the entire solution. From the parity observation, two cases emerge. If the number of negative elements is even, we can always pair them up and eliminate all negatives. In this case, every element in the matrix can be made positive. However, if the number of negative elements is odd, then no matter how many operations we perform, exactly one element must remain negative. This restriction fully determines our optimal strategy. To maximize the sum of the matrix, we follow a simple but effective plan. First, we conceptually convert every element to its absolute value and compute their total sum. Second, we count how many elements were originally negative. Third, we track the smallest absolute value present in the matrix. These three pieces of information are sufficient to compute the final answer. If the count of negative elements is odd, one element must remain negative. To minimize the loss in total sum, we should choose the element with the smallest absolute value to remain negative. Why does this work? Because flipping the sign of an element efficiently reduces the sum by twice its absolute value. By sacrificing the smallest magnitude number, we minimize the penalty. Hence, the final adjustment becomes absolute sum minus 2 times the minimum absolute value. Let us summarize the complete algorithm. We initialize three variables, a running sum of absolute values, a counter for negative elements, and a variable to store the minimum absolute value. We traverse the entire matrix once. For each element, we add its absolute value to the sum, count negatives, and update the minimum absolute value. If the number of negatives is odd, we subtract twice the minimum absolute value. Finally, we return the resulting sum. This approach avoids simulation entirely. Here is the first part of the C++ implementation. We initialize our variables and iterate through the matrix using nested loops. For each value, we add its absolute value to the total sum. This ensures we are always working toward the maximum possible sum. In the second part, we count how many values are negative and update the smallest absolute value. After traversing the matrix, we check if the negative count is odd. If it is, we subtract twice the minimum absolute value. The function then returns the final computed sum. The code is clean, efficient, and directly reflects the mathematical reasoning. This solution is extremely efficient. We traverse the matrix only once, giving a time complexity of big of n squared. We use only a few extra variables, so the space complexity is constant. This makes the solution scalable even for the largest allowed matrix size. The key lesson from this problem is that we should not rush into simulating operations. Instead, we must identify invariance, properties that never change. In this case, sign parity guides the entire solution. By combining mathematical insight with a greedy strategy, we arrive at an elegant and optimal solution. Thank you for your attention.